So the next important distribution on our list is normal distribution. Well, for the normal distribution, it has those three properties. It is bell-shaped, meaning the values start low on the left, then they peak towards the middle, and then they also go low again. Now, this distribution is symmetric about the mean, meaning the left side of it is a mirror image of the right side. And again, the area under the curve is 1, just like for all probability density curves. Now, the notation that we're going to use is x with tilde n, and in parentheses, we're going to have the parameters of that distribution, which is mean and standard deviation. As the next slide is going to show, the shape of the normal distribution is going to largely depend on the values of mean and standard deviation. So here we have a couple of examples. So we have three normal distributions here. So this one, the green one, it has the mean of 2.5 and the variance of 4. So which is the standard deviation of 2. Now, the orange one has a mean of 0 and the standard deviation of 1, and the blue one has a mean of -3 and a standard deviation of 0.5. So as you can see, there all of these three distributions, they have all of those three properties that we just discussed, which is they're all bell-shaped, they all are symmetric around the mean, and they're all their areas, their total areas equal to 1. So if the standard deviation is smaller, then our distributions are thinner, but they're taller because the total area is 1. If the standard deviation is larger, then they're wider, but they're also not as tall, but the general shape is the same. Now, in this section, we're going to talk about normal distributions in more details in the next section, in the next unit, Unit A. But in this section, we're going to focus on one of those normal distributions, a specific one, the orange one, where our mean equals 0 and the standard deviation equals 1. It's just one of, it's a special normal distribution, and it is called a standard normal. Well, let's talk a little bit about it. Well, in general, we use calculus to calculate those areas under the curve. And in order to calculate the areas under the curve, we need a function that describes that curve. So this equation that you see right here happens to be that function. And as you can see, that function is very complex, right? For calculations. But if you plug in, and as a parameters, it has mean and standard deviation. It has a couple of irrational numbers such as e and pi, but those are constants, right? So if we plug in mean equals 0 and standard deviation equals 1 into this equation, it will simplify tremendously. So this is called a standard normal distribution when mean equals 0 and standard deviation equals 1. Now, all other normal distributions are going to be basically compared to this standard normal distribution. Standard normal distribution is denoted by Z. Here's the notation that we're going to be using, X tilde Z, and it applies, it's a normal distribution with mean equals 0 and standard deviation equals 1. And question to you guys, what do you think? How many real life data sets will have a mean of 0 and standard deviation of 1? And if your answer is none, you're very close. Yes, I agree with you. I mean, I don't know any distributions whose mean equals 0 and standard deviation equals 1. So it's a distribution that's easier to use, easier to calculate values under the curve. So this is our standard normal distribution. Now, how do we calculate the values? All right. Let's talk about that. So here's our standard empirical rule that we already know. We know that between mean and within one standard deviation to the right, we have 34% of data values. So the probability that a randomly selected X is going to be between 0 and 1 standard deviation is 34%, and -1 is 34, so forth. That's we already talked about it. This is what we already know. Now let's use this information to calculate some of these values, probability values. So the first one, what's the probability that Z is less than 0? So we have 0 right here, and 0 actually divides this distribution in 2 equal parts. Remember, it's symmetrical. The left side is mirror image of the right side. So 0 is exactly in the middle. So the probability that Z is a variable, Z is to the left of 0 is 50%. So it's 0.5. Now, the next question, what's the probability that Z is between -1 and 1? So between -1 and 1 here.
We know that we have 34% of data, one standard deviation to the left of 0, and 34% one standard deviation to the right. So we're going to have 0.34 plus 0.34 equals 0.68. All right. The next question is asking, find the probability that the Z is going to be between 0 and 2. So again, just a reminder, Z represents number of standard deviations in a standard normal distribution. So this is the X value that's between 0 on the standard scale and 2 on the standard scale. So there we have 34%, which is 0.34. And between one standard deviation and 2 standard deviations, we have 13.5%. So plus 0.135. And when we put that into a calculator, we're going to get 0.475. All right. Next, question D. What's the probability that Z is greater than 1? Okay, so 1 is right here. So greater than 1 means to the right side. Okay, on the right side of this Z-score of 1, we have 0.135. So 13.5% translates into 0.135 in decimal form. We also have 2.35%. Again, when we convert it to a decimal form, that's going to be 0.0235, right? And also we have 0.15%. So this is a fraction of 1%, right? So it's going to be a really small value. It's going to be 0.0015 in decimal form. So we're going to have a plus 0.0015. And when we put this whole thing into a calculator, we're going to get 0.1. So far, we used the values that we learned in empirical rule, right?
Now, all of these z-values that we discussed so far, they are part of our empirical rule. Now, the question is, what are we going to do if we're asked to find the probability where and the z-value that is given to us is not one of those nice whole values. Now, statisticians have several different tools for figuring out these values. And in the next video, I'm gonna show you the tool that we're gonna be using in this class.